CIVL2210 Fundamentals of Soil Mechanics. Practical Group 33, Exercise 2, presented by Tom White and Naya Yamamoto. Exercise 2.1, Consolidation and Settlement. The purpose of this experiment is to demonstrate the effect of loading on drained and undrained soils. The apparatus was first loaded by weights. It was observed as the weights were added onto their apparatus, the water pressure table increased, whilst the actual water table did not increase nor decrease. After 5 kilograms of weights were added, the water pressure valve was opened and water was discharged through the valve due to the pressure built up in the consolidation process. Once the discharge completed, weights added to the apparatus were unloaded. The water pressure gauge was measured and recorded throughout the experiment. The results can be seen in these graphs. An inverse relationship is observed between the displacement versus weight graph and the stress versus strain graph in all 4 tests. In all 4 tests during loading, the water table did not change, whilst the pressure increased. This is due to the incompressibility of water. Due to compaction, the pressure water table remained constant after the initial drop in pressure from discharge for saturated water pearls and saturated rubber granules. No change in water level was observed during the loading and unloading phase of saturated gravel. This is due to the rigidness of the gravel holding up the weights. During the loading and unloading phase, the top of the dry water pearls did not recover to initial position after unloading. It appears the consolidation process has caused a long-term elastic deformation or a permanent plastic deformation in the pearls. Here is the fundamental equilibrium equation the system tries to achieve at all times when water is involved in consolidation and settlement, where the change in pressure of the beaker as the weights are added is represented by force over area, and the change in height due to pressure in the pressure gauge is represented by density times gravity times height. This exercise relates to real-world geotechnical problems such as soil compaction and its effects on porosity and soil strength, where due to compaction, the porosity decreases and hence decreasing groundwater flow rate, but the strength of the soil is increased. Furthermore, this exercise observes the effect on sediment due to discharge in different soils. Where gravel represents gravel, grinded rubber can represent coarse sand, and jelly beads can represent organic materials. It is recommended to investigate the effect on sediment due to discharge in clay soils, since this is one of the biggest problems in sediment. However, problems such as low discharge rate hinders clay being used in this exercise. Exercise 2.2, Slope Stability, Shear, and Effective Stress. The purpose of this experiment is to demonstrate the effect of water on slope stability, as well as give an introduction to the basics of effective stress. The following video is gravel filled to 100 mm and water filled to 100 mm, sliding with unsealed effective stress hole in the beaker apparatus. This video is also how sliding is defined in this exercise. The next video is the same setup except with the effective stress hole sealed. It can be seen with the effective stress hole sealed, the beaker apparatus did not slide at the same angle. So the next video increased the ramp angle to enable sliding action of the sealed effective stress hole beaker apparatus. This is a simple diagram explaining the process. When the parallel component of the weight is greater than the frictional force, the beaker will slide. The parallel component is increased. This is the diagram for when the effective stress hole is unsealed and water is allowed free contact with the ramp. As it can be seen, an additional force is applied onto the ramp. This is the pressure caused by the water. From the equation above, the effective stress is reduced as the water pressure increases. The results suggest similar as theorized. For open effective stress hole, the sliding angle is always lower than the closed effective stress hole. From the equation, it is suggested as weight is increased, the effective stress will also increase due to the total stress, if the water pressure stays constant. This can also be observed from the results with some errors. Thank you for your attention. The end.